Hello. Today we are going to see how you can create an odometry publisher, how to publish the odometry of a simulated robot, provided that you cannot calculate exactly the odometry from the wheels or else. So you would like to take this odometry directly from the gazebo simulation position that is provided of your robot. This could be very useful for robots that have a very complicated algorithm for calculating the odometry, or maybe robots that have legs and you have problems calculating its odometry. Okay, so the first thing, we are going to launch this simulation. We are going to work with the Kabuki robot. So here in the ROS Development Studio, I'm going to launch this Kabuki simulation. So I launch it, and then while the system is loading, then we wait just a few seconds. On one side we'll have here the simulation of the Kabuki, and then here in the center we have the IDE, where we are going to develop a node that publishes this odometry. Okay, here below we have a shell. We can communicate with the simulation, and the first thing that we need to know is how can we get the position of the robot in the simulator. For that, there exists a service in Gazebo that is around here that is called Gazebo get sorry, I cannot see it. There's Gazebo get model state. Exactly, here it is. This, if we call this service with a ROS service call, then it will provide us with the current position of a model that is inside of the simulation. So as you see, when we call this service, it requires us to provide the model name. In this case, that would be the model name that we have in the Turtlebot in my simulation. In your case, it will be your robot model name. Then I don't know this model, so I should put it there, the model, but I don't know. So what I'm going to do is just abort this and then call a different service provided by Gazebo. That this service is called Gazebo get wall properties. This other service provides a list of all the model names that are inside the simulation. And here it is a brick wall, the ground plane, and then the mobile base. So that's it. Mobile base is my name of my robot. So now again, if I call with a ROS service the Gazebo get model state, and I provide here the name of the mobile base, that is called mobile base, then it will provide me, yes, with all this information that is a pose with the position and the orientation, and then a twist with the linear and angular velocities. And this sounds like what we will need in order to publish an odometry. So what we are going to do is, in our node, we are going to first call the Gazebo service that provides the position, take the relevant data, and then publish that in an odometry topic. For that, I'm going to first create the package that will do all this, that will contain the node. Going to the Catkin workspace, then I'm going to call my package my odom publish. It depends on ROS.py. I'm going to do this using Python because it's faster. But you can do exactly the same with C++. So here it is, my package newly created, and then I'm going to create a new folder with the launch file will be there. And then there, and the launch file, I'm going to create, so the launch file. I'm going to call, for example, let's call it start the odom.launch. Great. So what do I have to do here? Let me enlarge this so we can work better. So here we have to do the usual thing for a launch file. We have to put the launch tag, and then the node one. And in the node, we need to put the name. Let's call this node, for example, odom pub. Yeah, Then the package, it's this one, the my Odom publisher. And then we need to specify the type that is the actual Python file that we will execute, that will contain the code of the node. Let's call it odom.py. And let's put the output on the screen. Great, we have it. So we save it, and then in the source directory, I'm going to create a new file that will contain the node that we decided to call it odom.py, yes, and the type, yeah. Okay, so first thing that we need to write here is the line that indicates that this file is a Python file that is executable. And this is required in order to make the system identify this odompy as an executable file for Python. And this is strange list of words that you can copy, pause the video in case that you need it. But you probably already know. Then next thing. The next thing that we need to do is to import, of course, ROS first. And then we need to import the odometry message that we are going to publish, because in odometry we need to publish odometry message, and those messages are included into the navigation messages package. So first we import odometry messages. Then next we also need to import from Gazebo the class that we will use to call the service. You see, this is a service, is different because this is the class that we are going to import for calling the service. But the problem is that I don't remember exactly what is the class that I had to put there. So no problem. Let's ask ROS about that. So let's call the service with some info, that request info, and to that service that we are going to call the get model state. It's Gazebo get model state. Then here we have, it's a message that is a message that is here in Gazebo messages, and it's called get model state. So from Gazebo messages.srv import get model state. This is for the whole proxy, but also we need to import the request class. That is exactly the same, get model state request. And you will see in a minute why we need those two. But it's very typical way of calling a service in Python. Okay, let's initialize first our node with ROS.py init node, and as we said before, we are going to call it odom pub. Next thing, so we have here, so let's create, for example, the publisher. So we need to create a publisher in which we are going to publish the odometry values that we will receive from the service. Calling it odom pub, and then publisher, and we need to specify the name of the publisher. I'm going to call it my odom, for example. And the type of messages now, of course, it has to be type odometry. Great. Next thing is we need to connect to the service. So for that, we need to do a proxy that connects to this Gazebo service in order to ask the proxy for this information. And for that, first we had to wait and just to check that the service is available in case that something goes wrong. Then our program will wait here. And for that, this is the sentence, wait for service, and the name of the service we are waiting to be working. So our program will wait there until that service is ready. Next thing is we create the proxy. Let's call the get model service. That's the connection to that service. And it's a ROS.py service proxy. Then we specify again the name of the service, that is gazebo get model state, and then the type of the message that we have to send. That, as you know before, get model state. Copy and paste. Great. Now we have the connection and the publisher. But still, so the thing that we'll have to do is to ask this service for the information, capture the important information from the message that we received from the service, and then create an odometry message, put this information inside, and publish into the odometry publisher. But first, I'm going to create here the basic message of odometry as an empty message. I need this in order to fill with the data. So here I have created an instance of odometry message that at this point is empty. I will have to fill it in a while loop. But also I'm going to create the header. The header is the information that contains the timestamp and the sequence. So I'm going to create an empty header first, and I'm just going to fill now the frame ID, because I know that is fixed this, and let's call this frame ID odom, for example. Yeah, there is an error here, the space, yeah, corrected. So this odom object is an instance of an odometry message, and it will contain a header. This header will contain this frame ID and also a timestamp that we'll have to modify in the loop all the time in order to actualize the time of every message that we are publishing. So now what we need? So we need to know we need to know the request to the service. Yeah. So we don't know here this message that we are sending to the service. We don't know what is exactly the structure. So for this purpose, we need to check it first. Then we need to create a get model state request. It's an empty one, but then we are going to fill it. This is the empty one that we are going to fill it with the model name, of course. And so the structure is like this: is get model state request, and then it contains a field that is called model name. And there is where I'm going to put my mobile base name. In your case, it will be the name of your robot. This is fixed, so we know that this is forever like this. So we have configured here. Then next, we are going to create a rate object for ensuring that the odometry is published, for example, let's say in 2 hertz. I mean, twice every second. And now we are ready. We are ready to implement the loop that we'll be doing all the time, calling the service of Gazebo, getting the information of the position of the robot, then modifying the odometry message with that data, and publishing on the topic. For that, we are going to use the shutdown function provided by ROS. So this loop will run until somebody presses Ctrl+C or ROS is shut down. So in this variable result, we are going to store the result that we obtain from calling the Gazebo service. So this get model service is the proxy that I created here. So we have to call it like this. We provide the model object, that is a model message that contains of course, the mobile base. So I'm going to put here the object model, and then this will do the call to the service and get the answer in the variable result. Great. So in that result, we have the information related to the position of the robot in the simulator. But, okay, I don't know exactly the structure of that. So let me just check the structure of that message result, because I don't know in which way this information can be used for filling the new odometry message that we have to publish. So very simple, ROS SRV show gazebo message, get model state, and we'll get the whole structure. Great, and we see here we have a geometry message pose and a geometry message twist. Here it is the part of the pose and here the twist, yes. And that looks very similar to what an odometry message has. So let's see, let's compare. Let's do a ROS message MSG show of the odometry message. And you will see, yeah, here it is, that still here, apart from the header, we have a header, of course, that indicates the timestamp and sequence. We have a pose here. It's saying geometry message pose that contains the position, the same as here in the message of the service. This pose, you see, is the same structure, is the same class. Basically, it's a geometry message pose. And then we have also, not the twist, sorry, the geometry message twist, exactly, is this part of the message that in the service is here. You see, this is the service information. Great. So this means that I can get those pose and twist from those and twist, pose and twist from the service, and then just put them straight into the odometry message. Here, substituting this pose and this twist with the information provided by the service. Very simple. So let's do it then. Okay. So now let's fill the odometry object dot pose, of course, because it's inside that structure. And we are going to fill it with the result.pose, as we have seen here in the here. Okay, yeah, something, yeah, is, where is it? Yeah, whatever. Here is the pose of the odometry. That one is the correct one, and here on the message, it is here. Yes. Great. So this is the two poses, how relate to each other. The pose in the service to the pose in the odometry message. And let's do the same exactly for the twist. Okay. And then result.twist is the same procedure. Great. Now we have the odometry pose, the odometry message filled with the proper information of odometry taken from the simulator. But now we have to change the stamp of the header. And for that, I'm going to use the ROS.py time now function. So now our header contains the current time where this message has been generated. So I have to assign this value to the odometry header. So every other message that we are publishing contains an actualized time of when it has been generated. And now the next thing that it remains is to publish. So let's use the odometry publisher that we have created here above and publish it. Then publish, and let's provide the object that we have to publish is the odom message. And that's it. Great. The only thing is that we ensure that we are going to have this loop at a frequency of 2 Hz by using the rate object. And that's it. Oh, the only thing is that this header, we didn't import this class here, so we need to add, of course, here. And the header, it's included in the standard messages of ROS. Great, we have it. File saved, and everything is in place in order to publish the odometry of the robot based on the position in the simulator. So I'm going to launch my node Here it is, and here it goes. Okay, yeah, so here we have a warning related to the queue size because I forgot to include this, but it's not important, the queue size. Yeah, there it is. This is not important. In the publisher, I didn't specify, but it's just a warning, so don't forget, in your case, to include the queue size value. So let's open a new terminal, and now let's see, and with an echo. First, let's see if our topic is there. Let's see, here it is, my odom. So it's there, great. So it looks like it's being published. Let's see if it's really publishing. Let's do an echo, and here it is. Here it is publishing, and as you can see, the values are 0, except from some decimals that are caused. Those decimals are caused by the noise in the environment of the simulation, but they are almost 0. Why? Because the robot is stopped since the beginning of our lesson. So, and you can see that the sequence is changing, the time is changing, but not the position. The position remains. Great. Let's open then another shell, and let's try to move it, the robot, and see if the odometry is being actualized. Let me just arrange this in a better way so we can see everything at the same time. Here is the odometry being published, it's still 0. And here I have the other terminal. And let me launch the Turtlebot keyboard teleop. It's a program that allows to move the Turtlebot around using the keyboard. So I launch it, and then you see here that it's 0 still, and now I'm going to move the robot. I'm pressing the keys, and you can see how the X and Y position, the X position is changing because I'm moving forward. Okay, so I move the robot forward, and the rest of the things remain 0. Now I'm going to rotate, and you can see, like in the orientation, the Z is changing because I have rotated. So it looks like it's working perfectly, our nodes, and so we have exactly what we wanted. That's all. Remember, you can send us questions, you can ask us things below in the comments of the video, or directly sending us an email. You can find more information in the notes of this video. Thank you very much for your attention.